How can certain systems follow all the rules of mechanics and still behave in ways that seem to defy conservation laws? Picture this. A perfectly rigid, unpowered bicycle rolls forward, the wheels spin, the body glides, and everything obeys Newton's laws. Now imagine trying to reverse engineer its motion. Predict where it will go just from its energy and position. You might expect that with full knowledge of the system's energy, mass, and constraints, everything should fall neatly into place. But it doesn't. Why? The answer lies in a class of constraints known as nonholonomic constraints, and they introduce a fascinating paradox into classical mechanics. Unlike holonomic constraints, which depend solely on the system's position, like a bead sliding on a wire, non-holonomic constraints are tied to the system's velocity and direction of motion. They can't be integrated into simple position-based equations. In other words, they are non-integrable. That one subtle distinction creates behaviors that can puzzle even trained physicists. Let's take the classic example of a rolling wheel. The wheel cannot slide sideways. It can only roll in the direction it's pointing. This rolling condition is a non-holonomic constraint. It restricts the wheel's velocity vector, not its position directly. The system has full energy conservation, and the forces are completely understood. Yet, if you try to derive its motion using only traditional methods, Lagrangian mechanics with generalized coordinates, you run into trouble. Why? Because non-holonomic systems don't conserve energy in the way we intuitively expect from systems without external forces. They often lack potential energy formulations or well-defined Hamiltonians. In fact, energy may be conserved overall, but it doesn't uniquely determine the system's future motion. The same total energy can produce many different paths depending on initial velocities and orientations. That breaks a major intuition that energy should limit or predict behavior. A more puzzling example is the Chaplygin Sleigh, a simple sled-like object with a blade or skid that prevents lateral motion. You give it a push, and it doesn't just slide and slow. It begins to curve, drift, even spin, depending on where you applied the force, all without violating Newton's laws or losing energy. There's no friction, no hidden damping, just a non-holonomic constraint, quietly warping the system's trajectory in ways that seem to emerge from nowhere. You might ask, doesn't this violate conservation laws? Not quite. These systems still obey Newtonian mechanics, and their total mechanical energy remains constant, but the mathematical tools we normally use, like energy-based variational principles, don't apply cleanly. That's the paradox. These systems play by the rules, but the rules don't give us the full picture. In technical terms, the paradox arises because non-holonomic systems can't be derived from a variational principle. Unlike holonomic systems, where we minimize action, as in Lagrangian mechanics, non-holonomic constraints introduce velocity-dependent restrictions that make the standard Euler-Lagrange formalism insufficient or misleading. The trajectory isn't the one of least action, it's the one permitted by an evolving set of kinematic limitations. Why does this matter? Because non-holonomic systems are everywhere in robotics, vehicle dynamics, spacecraft motion, and even in biological systems like snake locomotion or willed bacterial swimmers. Understanding their paradoxical nature allows engineers to design motion planning systems that don't rely on traditional energy-based models. It also deepens our appreciation for how complexity and emergent behavior can arise from simple rules, just by making those rules depend on direction and velocity instead of just position. So, what does the non-holonomic constraint paradox really teach us? That energy alone doesn't always dictate motion, that direction matters, and that even in classical mechanics, often seen as the realm of predictable clockwork systems, there are surprising corners where intuition falters and the rules of the game bend in unexpected ways. The non-holonomic constraint paradox refers to the unintuitive behavior of mechanical systems subject to non-integrable constraints, those that depend on velocity rather than just position. These systems can exhibit motions that appear to violate conservation of energy or momentum, even though the forces involved are ideal and the equations of motion are rigorously defined. The paradox lies in how constraints that limit velocity, not position, generate complex behaviors such as unidirectional drift trajectory dependence, and controllable locomotion without obvious energy input. A rolling coin or a unicycle can move forward without slipping, constrained by the no lateral velocity condition. Yet its motion evolves in ways that seem to extract directional motion from internal It's like watching a snake wiggle forward while always in contact with the ground. How does it move without pushing off anything? A non-holonomic constraint is a kinematic restriction on a system's velocity that cannot be expressed as a derivative of a position-based equation. These constraints typically arise from rolling contact, knife edge motion, or steering conditions, and are not reducible to geometric constraints. Unlike holonomic systems, which evolve on well-defined surfaces in configuration space, non-holonomic systems are constrained in how they navigate that space, not in the space itself. A rolling wheel must move tangentially to its axis. It cannot slip sideways. This condition is velocity-dependent and cannot be converted into a positional constraint without losing information. It's like telling a skier, you may only move where your skis point, not limiting where they can be, but how they can get there. In non-holonomic systems, the constraints do work like effects without dissipating energy because they redirect motion rather than resist it. This leads to situations where internal motions, such as shifting masses or steering wheels, produce net movement or reorientation without external forces. While energy is conserved globally, its expression in observable translational or rotational forms may not follow typical intuition. The Chaplygin Sleigh, a rigid body sliding with a knife edge, changes direction when rotated, even though no net force is applied. Its energy remains constant, yet its momentum seems to shift unpredictably. It's like spinning a boomerang and watching it veer sideways without anyone pushing. It moves because of how it's constrained. Non-holonomic systems illustrate how constraints shape dynamical flows in ways that are highly path-dependent. These systems do not conserve phase space volume in the traditional sense, leading to emergent behaviors like non-reciprocal locomotion, asymmetric control, and motion from cyclic internal changes, known as geometric phases. In robotics, these insights are essential to designing snake robots, wheeled vehicles, and underwater gliders that exploit non-holonomic effects to move. A robot with internal rotors can reorient itself or crawl without touching external surfaces by manipulating its internal degrees of freedom under non-holonomic constraints. It's like rowing a boat in molasses by only shifting your weight. The path matters more than the power. Though non-holonomic constraints are ideal, they do not dissipate energy, they redistribute energy across degrees of freedom. The system's total kinetic energy may remain constant, but it shifts between modes in non-integrable ways, leading to non-conservative evolution of momentum. This results in drift, precession, or biases in motion that accumulate over time without violating the laws of mechanics, but requiring more careful accounting. A robotic ball with an internal flywheel can roll in a direction simply by spinning its internals, changing its trajectory through constraint interaction despite constant total energy. It's like balancing books on a seesaw. No one lifts anything, but the center of mass shifts mysteriously through clever motion. From an information perspective, non-holonomic systems demonstrate that constraints encode rules about motion, not just limits on position. They form a submanifold of admissible velocities, and motion becomes an information-driven pathfinding problem in this reduced space. Planning motion in such systems requires non-intuitive trajectory designs, as the final configuration depends not only on endpoints but on the full path taken. Parallel parking a car is a non-holonomic problem. The car cannot move directly sideways, yet with a specific sequence of forward and backward motions, it achieves lateral displacement. It's like playing chess where the piece must zigzag across the board to reach a square 2 spaces away. Legal moves don't follow direct lines. Understanding non-holonomic constraints has enabled breakthroughs in robot locomotion, spacecraft orientation, and animal biomechanics. Engineers now design control algorithms that exploit rather than fight these constraints, enabling efficient motion in constrained environments. In nature, organisms like snakes, bacteria, and fish use constraint-compliant gaits to achieve motion without traditional propulsion. Snake robots use lateral undulation, a non-holonomic strategy, to move over complex terrain by pressing against environmental constraints. It's like dancing across the floor with your feet glued in a line. You glide forward through rhythm, not stride. Non-holonomic systems resist intuitive analysis and often defy conventional control theory. Their behavior depends on non-integral differential equations, making them harder to simulate or stabilize. Designing control inputs requires understanding Lie brackets, non-commutative geometry or geometric phases, placing non-holonomic control at the intersection of mechanics and abstract mathematics. To stabilize a non-holonomic mobile robot at a point, one must use non-traditional control laws. Standard Liopono-based methods often fail. It's like programming a dancer with only sideways steps to spin in circles. You need clever choreography, not brute force. Non-holonomic mechanics will play a major role in adaptive robotics, autonomous vehicles, and neuromechanical prosthetics as machines enter constrained environments, cluttered cities, collapsed buildings, deep sea terrain. Mastery of constraint-driven motion will become essential. Further, non-holonomic thinking reshapes how we understand lifelike movement, offering a bridge between mechanics and biological control strategies. NASA is exploring non-holonomic strategies for Mars rovers and legged robots that must traverse uneven terrain with minimal energy expenditure and reduced actuator count. It's like discovering that the key to motion lies not in power but in pattern, learning to move by obeying clever rules instead of brute mechanics.